In this video, we're going to look at finding points of intersection of linear functions, or lines, and quadratic functions, or parabolas. The first thing to recognize is that lines and parabolas can intersect at 0, 1, or 2 points. If this is my parabola, I could have a line like this that doesn't intersect it at all. I could have a line like this, which, if I drew that a bit better, would only intersect it at one point, this point right here. And I could have a line like this that intersects at two different points, here and here. So lines and parabolas, linear functions and quadratic functions can intersect 0, 1, or 2 times. Here's an example of a kind of question that we can get. Find the points of intersection of this parabola and this line. Now recall that to find the point of intersection of two functions, we set them equal to each other. So I take x squared minus 8 and set it equal to 2x plus 7. And that's because for them to intersect, at that point, the x and the y values have to be identical. So this y value, let's call that y1, has to be the same as y2. So we set them equal to each other. X squared minus 8 is equal to 2x plus 7. And now we need to solve for the x values that would make that true. Before we do that, let's just think about what's going on here graphically. If I were to sketch this, I could sketch something like this. Here's y is equal to x squared minus 8. And I've got a straight line, let's say something like that, which is y is equal to 2x plus 7. And because this is a parabola that's been moved downwards by 8, and this is a line with slope of 2 and y-intercept of 7, I can imagine that it looks like they should intersect twice. I should find two solutions to this equation, and that's why drawing a sketch can be helpful in figuring out the solutions. Now let's figure out the actual solutions. If y1 is actually equal to y2, we'll be able to find a solution at the point where, at the x value where they are equal. So moving everything to one side, I get x squared minus 2x minus 15 is equal to 0, and now I need to solve this quadratic equation. Notice that this quadratic equation is the same thing that I would be doing if I were trying to find the x-intercept of this parabola on its own. In other words, I've taken this more complicated question, find the point of intersection of this parabola and this line, and turned it into this simpler one, which is find the x-intercepts here and here of this parabola. And that's because these two lines, the top line and the second line, are completely algebraically equivalent. I can manipulate this to come up with this, and so the solutions are the same. It's much easier to find the x-intercepts here. I just do that by factoring. This factors to x minus 5 times x plus 3, which is equal to 0. If the left side is equal to 0, then x is equal to 5 or negative 3. That means for this parabola, which I've drawn down here, this is the parabola y is equal to x squared minus 2x minus 15, the x-intercepts are negative 3 and positive 5. That means up here, for this system of a line and a parabola, the first point of intersection is at x is equal to negative 3, and the other one is at x is equal to 5. Now I still don't know what the full point of intersection is because I need to find the y values. Recall that we found that x squared minus 8 is equal to 2x plus 7 when x is equal to negative 3 or 5. So I just need to sub both 5 and negative 3 back into the equations to find y. It doesn't matter which equation I sub them into because they'll both give me the same answer. And you can check that by doing both of them. But I'm just going to sub into the easier one, for me, the linear function. So if y is equal to 2x plus 7, if I sub in 5, I get y is equal to 2 times 5 plus 7, which is equal to 17. If I sub in negative 3, I get y is equal to 2 times negative 3 plus 7. Negative 6 plus 7 is positive 1, so I get y is equal to 1. That means the points of intersection are 5, 17, and negative 3, 1. And you can see that if I plugged 5 into this one, I would have gotten 25 minus 8 is 17. If I plugged negative 3 into this one, I would have gotten 9 minus 8 is 1. So we get the same answer. So that's how you find points of intersection between parabolas and lines. You set them equal to each other, bring everything to one side, factor or use the quadratic formula to solve that equation, and then sub back in to find the y values. Let's look at another example. Here we're asked how many times does this parabola intersect this line? So once again, let's assume that they do intersect and set them equal to each other. If they intersect, their y values are the same, which means that the y value of the first one, 3x squared plus 12x plus 14, has to be equal to the y value of the second one, which is 2x minus 8. Once again, I'm going to move everything over to one side. So I get 3x squared plus 10x plus 22 is equal to 0. Again, what that means is the points of intersection of this parabola and this line are going to be the same as the x-intercepts of this function. So now we just need to find out how many x-intercepts this function has. And recall that because we're not being asked to solve for what they are, just how many there are, this is a discriminant question. So we want to find the discriminant of this parabola. Remember that the discriminant is equal to b squared minus 4ac, and in this case, a is equal to 3, b is equal to 10, and c is equal to 22. Now if I sub those in, I get the discriminant is equal to 10 squared minus 4 times 3 times 22, which is equal to 100 minus, and this comes out to 264. Therefore, the discriminant is equal to negative 164. Recall that the discriminant is the part that goes under the square root sign in the quadratic formula, so if this is a negative number, we're not going to get a real number out of the quadratic formula. That means this has no x-intercepts, and that means that where we started from, this parabola and this line don't intersect. So, therefore, there are no points of intersection because the discriminant is less than 0. So there are some examples of questions you might come across involving the intersection of lines and parabolas.